Okay, so it's my pleasure to introduce our very own David Silvester. He will talk about IFIS, a computational laboratory for investigating NLA problems.
Okay, thank you, Stefan. I hope everyone can hear me, and even people in the distant places out there can also hear me. So yes, it's a big thrill, actually, to be standing in front of you. Mostly because I really like talking to people rather than to blank screens. And so this is my third talk in 3 weeks where I've actually seen faces, and the thrill just doesn't go away. Yeah, I changed the title slightly. I tried to put off as many people as possible by mentioning incompressible flow, but really, like, center of attention here is numerical linear algebra, being the theme of the meeting. The second theme, of course, is Professor Hyam, who I have known for a very long time. And so I'm going to talk about Nick in a couple of ways, but I want to express my relationship with Nick in terms of a diagram. Okay. So this is my relationship with Nick, well, mostly. Okay. So it's not a function, it's a relation. Let's be clear about this. So my relationship with Nick is something like this. And I'll give you two examples of this, but basically, if you engage with Nick, you get more out than you put in. Okay, that's the moral that I'll go through later. So I'm talking about software here. This is as close as I can kind of get to numerical linear algebra. So some of you might have seen or heard or even used IFIS. Perhaps I can ask the audience if you've actually used IFIS. Can I have a, so we have some more than last week. That's good. So for the rest of you, I'm going to try and convince you that maybe you want to perhaps take a look at it. So the software is a MATLAB package, or written originally in MATLAB. It runs completely 99% compatible with Octave. It was associated with actually writing a book, which we've heard about briefly from Andy. So this is a book with Andy Wathan and Howard Ellman. And when we started writing this book, one thing I was keen on, more than keen, evangelical about, is the idea that if you write a book and generate results, then people should themselves be able to generate those results. All the figures in the book should be generatable by anybody reading the book. And so this software essentially went with that development. And so the three developers of the software are myself, Howard Ellman, one of the book co-authors, and Alison Ramage, who is at Strathclyde. And one notable feature about this is that this was written in about 2000, and the three authors still have the same affiliation. Okay, we haven't moved. That tells you something. Read into that what you will. I'm still in Manchester, Howard's still in Maryland, Alison's still in Glasgow. There are two papers which have been written about the software, and they coincide with the editions of the book. So the book came out in 2005. It took 2 years to actually formalize the software. I would like it to have been on the same day, but there was a paper eventually published as an algorithm in ACM Toms, which I have a very soft spot for, because at that time it was just about the only journal where you could submit code or algorithms and get it published. I can put it as such. And it's a very highly respected journal, still is today. The second edition of the book came out in 2013, and coinciding with that, I can see Des is sitting over there, partially responsible for this. Siam Reviews introduced the idea of publishing software reviews. And I think, if I'm not wrong, this is one of the, probably the first paper, which was actually a software review published in Siam Review. So that was 2014. So I don't say anything else about the software. You can go and look at these two references where it's described. I want to just say, before I go there, something about this picture here. So how did I learn about writing software? Well, I learned about writing software indirectly through Nick. And how did this come about? It came about because I think, as we've heard already, I think it was 1992, Nick had a sabbatical in Cornell. And me and Nick, we got on pretty well, I would say, at that time. We still do. And Nick said to me, by the way, I'm going on sabbatical next term. And he taught a course on the MSc called Mathematical Software. He said, would you like to give it? And I said, but look, I'm already teaching 2 courses, Nick. And three is a bit much even for me. He said, it'll be fine. I've got complete notes. Everything will be ready to give. And it was. So complete notes. I really didn't have to do very much apart from learn myself from these notes about what it takes to write good software. So yeah, I attribute my software writing skills to actually Nick. So that's what I mean about this. I was doing him a service, but I got more out of it than I was actually putting into it. I'm trying to think back of who was there at the MSc. Bobby Cheng was actually around at that time, who's now at the MathWorks, who writes software for a living. I'm not sure if he did my course, my version of the course, or Nick's, but it was around that time. Okay, so I'm going to do the opposite of what Jack did by looking to today. I like the idea of looking backwards and the idea of reproducible software. So this is a picture of IFIS in 2001 running on my computer at the time, which is, some of you might recognize it, it's the original iMac Bondi Blue, the machine that saved Apple computers. It's running MATLAB 5.2. And I've ran the same experiment a couple of weeks ago on my current laptop and just checked to make sure I still get the same results. And I do, well, to within 15 decimal places, unit round off. So that's quite interesting. So 2001, well, he's not here. There's at least one member of this group who wasn't even born in 2001. That's a long time ago. And I can still generate those results today. If you want a little bit more detail, going the opposite of where Jack was going, and look at my computer in 2001, you can see that it came with 32 megabytes of memory. And the operating system takes 14.8 of those megabytes. So I've only got about 16 left to run MATLAB. The computation, so this is, the computation is one of the first test problems in IFIS. So it's the Poisson equation with constant right-hand side on an L-shaped region. And the picture you're seeing is the solution and an estimate of the error, which is automatically calculated, which shows you what the singularity is in the solution.
You know why your answers are not bitwise the same? Is it a new algorithm or is it some randomness? Or you said there was floating point error for the. I mean, if you run the same software on the same IEEE standard, if everything
was the iMac IEEE standard. It was a PowerPC chip. Yeah.
You really think that's the difference? The chip?
I don't know.
Everything else is the same as far as you know.
I'm going to double check this, okay, when we finish this talk. And the other thing to say, I did some timings. Okay, so the linear system here is dimension about 1,000. It's 1,000 by 1,000 sparse matrix.
IEEE standard was in 2000.
So 1,000 by 1,000 matrix, and in 2001, it's about 0.1 of a second using backslash. And then last week, now my laptop, you can't see it so clearly, I will magnify it. That's 32 gigabytes, by the way. That's 1,000 times more memory. And it's the same solution. The graphics has changed a little bit in MATLAB over the years. This isn't MATLAB 5.2 anymore. But at the time, it's about 1,000th of a second, so it's 100 times faster. So, so I like that. I like the fact that you can run IFIS 20 years ago and still get the same result, essentially, today. So if you're doubting its utility, then let me ask this question: why might IFIS be useful to you out there? And this, I think, is the key answer. So, and why it's actually used, it's used essentially as a source of reproducible test matrices in terms of the linear algebra community, not the PDE community here. So people use it in this community because they can generate test matrices and try out different algorithms. Okay. It's particularly good at certain categories of test matrices. A key thing is, though, it's of arbitrarily large dimension. In 2001, 1,000 by 1,000 matrix was a large matrix. And today, the sparse matrix dimension could easily be 1 million, and it would do it in a few seconds or less. Okay, so your problem scales with the era you're operating in. And it's particularly good for generating saddle point matrices, symmetric indefinite matrices, sometimes singular, sometimes not. They're associated with steady state Stokes flow. I'll say something more about that in a moment, but also PD constrained optimal control. So there's a piece of IFIS that was written by John Pearson, who was Andy's student at the time at Oxford, and part of his PhD, actually. There's the start of his work is on Laplace-based optimal control. So that's also in IFIS. The main part of IFIS, in some sense, is Navier-Stokes equations. That is, you get non-symmetric matrices with a special property of having a positive definite symmetric part. So you get those with steady state convection diffusion problems if you discretize convection properly. It's a skew symmetric operator up to boundary conditions, or in a saddle point structure, linearized Navier-Stokes equations, steady state Oseen flow. Now, for the younger people out here, you don't get much credit typically for writing software. And not that I'm competitive in any way. Okay. I am actually a little bit competitive. I am a little bit competitive. So how can you kind of like see how good you are in terms of your software? Well, there's this great site, which I'll take you to. It's called SW Math, which it may or may not go to. It didn't like that, did it? I'll try that one more time. Okay, here it is. And you have written some software. Why don't you try typing in the name of your software, if you can spell? Okay, IFIS, query. So SW Math was funded, I think, originally from Oberwolfach. It's together with Karlsruhe. And you can get some measure of how useful, as it were, your software is. And here it is, top of the pops, IFIS. You get a nice word cloud. And, well, this is a measure of it. Since it started, 253 journal articles have actually cited IFIS. So I'm quite happy with that. That tells me that something good is happening. Because for everybody who actually cites IFIS, I'm sure there are 4 or 5 other people who can't be bothered. They're using it anyway. So, so try it with your software. How many hits do you get? Okay. I won't say any more about that other than I like SW Math, but then also back to Tom's, you don't actually reference the software, you need to write a paper about it. That's why you need Tom's. These are not direct references to the URL of the software, they're references to the ACM Tom's article, okay? Good, so we can see that we're doing something good with SW Math. So what are the distinctive features? So I want to just now focus in on one thing, but if I had to summarize, like, what does IFIS give you? These are the 4 kind of themes. There's a special version of MinRes. It gives you fast solvers for flow problems to investigate these matrices, fast solvers for PD constrained optimization. And over the last 10 years, my research interests have really moved into PDs of random data. And there's a simple extension, or relatively simple extension to IFIS called SIFIS, where you could explore these test matrices also, or generate test matrices. And I should say that essentially all the research papers I've written since this time, results are reproducible in that you can run IFIS and generate them for yourself. So I want to just concentrate in 5 minutes, I have 5 minutes, on one thing. So I'll talk about MinRes. So I can do this, I think, fairly quickly. So this is a generic saddle point problem of physical importance. These are Stokes flow. So the equations at the top, U is the velocity of a fluid, P is the associated pressure, and the fluid is incompressible. So div u equals 0 is the incompressibility constraint. And that is a saddle point problem. So if you write it in functional form, which is done in the next line, you have a weak formulation, then you have this characteristic AB kind of structure. It's saddle point because it's got a 0 block, because there's no pressure in the incompressibility constraint. So if you look at the approximation theory for this, then you end up with an optimal approximation that is up to some constant C. You have the Galerkin solution is the best approximation from the subspace up to this constant C. C is going to depend on something called the im sub constant. So what does this min-res do? Well, first of all, you need to have some measure of how to measure things, the norms. So let's refer to this graph norm as the natural norm, because that's where we measure the errors in the approximation sense. And so what this min-res code will do, it's an iterative algorithm. It'll construct iterates which converge rapidly in such a way that you stop at exactly the right point. That is, when the algebraic error, that's this one here, is commensurate with the digitalization error. IFIS has built-in error estimation telling you how close you are to the solution of the PDE. So if we can figure out the constant here, the equivalence constant, we can be precise about when to stop. And IFIS does this actually automatically. And the key ingredient to this is this famous im sub condition. This is a compatibility condition in the Stokes sense between the velocity approximation and the pressure approximation using finite elements. You can't just arbitrarily mix these two things. In particular, if you choose the same thing for velocity as pressure, it goes wrong. It's not stable. So there are classes of stable approximations. Typically, the velocity approximation is one polynomial degree richer than the pressure. So this is a stable element in 2 dimensions. This is a 9-node velocity element, biquadratic for each degree. In 2D, there'll be 2 degrees of freedom at each node. And we have a discontinuous linear approximation of the pressure. So 3 degrees of freedom in each element. So to connect with linear algebra, we need some matrix version of the im sub constant. That's quite straightforward once you know what you're doing. This is associated with the Schur complement, what fills in this block when you block Gaussian elimination, BA minus 1 BT. And this has to be spectrally equivalent to the underlying norm in which you're measuring the dual variable, the pressures. That's this norm here, associated with the matrix M. Now, in the Stokes sense, the upper bound is kind of for free. It comes from the continuous problem, but the lower bound is not. So you kind of have an eigenvalue problem you can compute on any given mesh, which tells you gamma or gamma squared. Okay. But what we need to do in the software is compute this kind of on the fly. Okay. So how can we do that? Well, first of all, you need to have preconditioning done correctly. So I want to make one point about preconditioning. Andy, I'm sure, has made this point many times, but it hasn't probably quite sunk in yet with everyone. So we're going to measure things in this energy norm, natural norm. Sorry, not energy norm. It's a natural norm. And that's associated with these 2 matrices, A, that was in the original problem, and this approximation to the complement, spectrally equivalent to it, this matrix M. For the element I showed you, M is a diagonal matrix, the mass matrix of pressures. And there's only one way to do preconditioning of this problem. You might think about incomplete factorizations or something algebraic, but the right way to precondition this problem is to do what's called operator preconditioning. And this has been written about by several authors, but the best version of this is a paper by Mardal and Winter, 2010. And they tell you how to do it. And it's related to the continuous problem. So what you want to do is have a precondition that works at the continuous level. And that involves mapping onto the dual space and back again. So if this is my operator, which is essentially taking me to the dual space, the inverse mapping is the inverse of this matrix, but we're allowed to cheat and have something which is spectrally equivalent to that. That tells us how to do preconditioning. So what we get from this preconditioning is not a reduced condition number. It's the wrong thing. What we get, if you have a perfect preconditioner and you put the Schur complements in here, you have 3 distinct eigenvalues. You have one cluster at 1, a cluster at the golden ratio, and it's symmetric about a half. There'll be another cluster on the left. because you preserve the inertia of the system. And for this system, if nu is the number of velocities, you have nu positive eigenvalues, np is the number of pressures, you have np non-positive, could be 0 eigenvalues. So you're preserving the inertia. So preconditioning is only about clustering. It's not about reducing the condition number. Okay, so back to min-res very quickly. So I say I want to balance these errors. So what I'd like to do is measure the residual in the right norm. In min-res, the residual is minimized. But that's the wrong norm. If A was symmetric positive definite, we'd be minimizing the A squared norm of the error. We want to minimize the A norm of the error. However, when we precondition in this operator sense, we minimize a different norm, the M norm of the error. And when you translate that into the iterates, it's the MA norm. And remember, MA is essentially identity. So it is the A norm of the error. So you automatically minimize the right thing by running min-res with this preconditioner, and the thing that's been minimized is exactly what you want to minimize. But you don't know the equivalence constant in the bound, because you've approximated M, BA minus 1 BT by M. So you need to do two jobs now to precondition this operator. You need to precondition the M part and the A part. This is a diagonal matrix, that'll be straightforward. What about the A part, this biquadratic approximation of the Laplacian? Well, this is pretty standard now. It wasn't when we started writing the code. You need some kind of algebraic multigrid. So again, built into IFIS is an algebraic multigrid preconditioner, which gives you spectral equivalence to the inverse Laplacian with order n work. To affect the action of the preconditioner, you only do order n operations. That's the number of, essentially the number of non-zeros in the matrix. And so this code was developed by Jonathan Boyle, Jennifer Scott's also here. It was developed actually in IFIS, but then implemented in real life in Fortran in this routine HSL MI20. So that's another thing you get in IFIS. So how does it work? Well, if you precondition this operator, this is a biquadratic operator. It's a little complicated because you don't have anything like an M matrix, because you have different connectivity of the degrees of freedom. This vertex connects to 4 elements. This connects to 2. This only connects to 1. You don't have a nice sign pattern in any way. Nevertheless, algebraic multigrid in this Ruger-Stubben sense is still spectrally equivalent. You have a parameter that you can vary, which is the number of V cycles. That's the number of times you go through the levels of meshes using something like Gauss-Seidel each iteration. So this is kind of like bounds. So if we have a really stretched grid, the equivalence isn't so good. But if you do more V cycles, for example, on this grid, 2 V cycles is usually fine. Okay. And this is independent of the mesh, independent of the digitization that we're talking about here. No matter how fine your mesh is, you're going to have these equivalences. So if I just give you one example. So this is the classical Stokes test flow problem. It's flow in a driven cavity. It's symmetric because it's Stokes flow. And you need resolution in 4 places. You need resolution in the top 2 corners because the pressure, there's discontinuity in the velocity at the top. So the pressure is actually singular, infinite, if you like, at the corners. But also the most interesting aspect of the flow of these recirculating eddies. There's an infinite sequence of these going into the corner. I've only shown you the first one. And you need stretch grids into the corners to resolve these. Okay. I'm running out of time. In fact, I've run out of time. So I'll give you the details offline. You can run this experiment. It's built into IFIS. And what happens is you estimate the input constant on the fly as you're going using properties of min-res. You work with the harmonic Ritz values, which are computed on the inside of the Lanczos process. From that information, you get estimates of the interior eigenvalues. And then you can reverse engineer eigenvalue bounds, I proved with Andy, to get an estimate of the input constant at every iteration. And the harmonic Ritz values converge really fast in interior eigenvalues. So it works well. Does it work? Here's just, this is like a coarse grid. So this one here, this is min-res converging in the right norm. This is my estimate of the energy norm, which is just multiplied by the inverse of the unit constant, which is about 0.2 for this domain. It's a square domain. So these will eventually become parallel because I'm going to converge to this value. And I'm going to stop here because I'm going to estimate the discretization error at every step. I'm going to keep going just to show you what happens. But this is my estimate of the error at flat, because now it's saturated by the discretization error. So I'm going to stop right here. That's the point, when these two cross. So I'm only going to do 9 iterations. There's no point doing any more because I'm just going to reduce the algebraic error. Whereas if I refine the grid, 2 grid refinements, I keep going for longer. I now do 20 iterations. And at this point, the error is now smaller. I've reduced the error from here to here because I've got a finer grid. So yeah, my final point, sorry, Stefan, too. This is the reference. I want one more thing to say about Nick and this thing here, which I'll share with you. I have other stories I could say about Nick, but they're not suitable for this Zoom audience. You have to talk to me at dinner later. But this story I will share with you. It's on this theme. So, so Nick was appointed in 1985, but the job was advertised in 1984. And there were a short list of, I think, 5 candidates. It was me and Nick and 3 others. So in that sense, we were competitors for the job. The interview was in May, and I had a girlfriend at the time. I was living in Abingdon. I was working at Harwell. And I booked a holiday from Harwell in Crete for a week. And you couldn't move package holidays as they were then so easily without a big financial outlay. And the interview date was right in the middle, Wednesday. So I had to make a decision. Do I go to the interview or do I go on holiday with my girlfriend? And so I decided to give up on the idea, leaving the path open, of course, for somebody else to get the post. And this bit about more out. Well, a month later, I was interviewed for a second job in Manchester that you missed, which I got. And the person I went on holiday with, of course, I married 3 years later, and we're still married. So 2 arrows at least coming out. Thank you for listening.